Hello everybody and welcome to another video. Today we're going to be talking about number bases and how to convert between two different bases. So first question you might have is, what is a number base? So when you think about numbers that we use every day, you're mainly going to be using something called the decimal system, which is base 10. So 963. This is base 10 because you have in each digit, there are 10 different possibilities, 10 different characters that can be used to represent that digit. So in decimal, this is equal to 3 times 10 to the 0, plus 6 times 10 to the 1, plus 9 times 10 to the 2. And that's, just basic stuff. So once again, you have 10 different possibilities. You have 0 to 9, which is 10 characters. Some other different bases you might have are hexadecimal, which is base 16, and you might see this written as 0xff. That actually represents the number 256, and this is equal to f, which is now another, which can be used to represent a character or a number or a digit, rather, in hexadecimal, because there are 16 different. So you have 0 to f now. So this gives you 0 to 9, which is 10, and then A, B, C, D, E, F, which is another 6. You have 16. Now, another one you might know, or probably know, is binary, which is just base 2, and you only have 0 and 1, because there are only 2 different possibilities there. So yeah, that's pretty much number bases. And in computers, well, I know in C++ you can do this, where you can write a number in any base as long as you have this right notation, and it will convert it into bytes, because it can convert anything into bytes as long as it has the right notation, but it doesn't really store that representation in that base. So for example, we couldn't just say, oh, computer, give me this number in hexadecimal. You would have to test, oh, is it 0xff, and if it is, print out 0xff, and so on. So we're going to write an algorithm today on how to convert between two bases. Alright, so let's look at a general case here on how to convert between two bases. So let's say that we have a number a, and it's in base, that's a disgusting A, I'm sorry about that. And we want to convert it from base x to a number c in base y. So once again, or not once again, there's going to be 2 steps to this process no matter how you do it. You're going to have an intermediary base, which will be in between the two bases, or doesn't have to be in between the two bases. But we're going to use decimals just because we know how to do division, integer division, and stuff like that with decimals, but we don't really know how to do it with binary numbers or some other system. So first step is we go a base y or x to some number b base 10, and then the second step is b base 10 to c base, and you have to split it up like this, otherwise it won't work. Or you probably could find a way to make it work, but it would require a lot of extra conceptualizing, and it's not really what we're here to do. Alright, so let's represent our original number as its, or let's look at its individual digits. So we're going to say this is equal to a to the n, a n minus 1, all the way to a to the 1, or a sub 1, a sub 0, where each of these are individual digits in our number. So these are all digits. Now, each digit in decimal will have some value based on its power or its order. So that number there, that subscript, we're going to call it k. So we're going to say b base 10 is equal to the sum from k is equal to 0 to n, where n is the length minus 1 of the string, or the number of digits, not the actual value, the number of digits, which might not always be the length of the string. So a k times or times x, damn it, ak times x to the k. So if we looked at our base 10 number and we plug that in and convert it back to base 10, what we would get is the digit 3 times the power, which is 0, or it's the 0th digit essentially going from right to left. So 3 times 10 to the 0 plus 6 times 10 to the 1, blah, 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 and you get your decimal value. So that's the decimal value. Now to convert from decimal to some other base, it's not too hard, but it's a little more, it's more time consuming because you have to do repetition. So first thing you're going to do is you're going to find the highest power of y in decimal. So I'm just going to put a y sub 10 there, such that, and we'll call this power m, such that y to the m is less than b base 10, which is also less than y to the m plus 1. We're essentially just finding the largest power that is just below the base 10 number. And next we're going to repeatedly divide. So divide by a y to the m minus minus. So we're going to be subtracting 1 from the exponent every time. The quotient becomes the character. And this is integer division. So, and then the quotient becomes that, then the remainder, you carry the remainder over to the next division. And then essentially you're going to repeat this process until the power m is equal to 0. So you're going to go from m, the original, to 0. So let's say m is 4, you go m is equal, or you'll go b to the b base 10 divided by y 4, get the quotient, put that in the number or in the string, and then you get the remainder and carry that over. All right, let's do a couple of examples here, keeping that algorithm in mind. Let's say we have a binary number. It's 1 0 0 1 0 0 0 1 base 2, and we want to convert it to some number c base 16, which is hexadecimal, like I said. So we're going from binary to hexadecimal here. So the first step is we want to go from 1 0 0 1 0 0 0 1 2 to a b base 10. And this is relatively easy. All you got to do is you just got to add the numerical values and then multiply them by the power of the base, where the power is the, where the exponent is the number, is the digit, or the number digit. So we're going to say 2 to the 0, 2 to the 1, keep going, 2 to the 4, 2, and then 2 to the 7 at the end, like that. And we're going to say b is equal to, now you see where the sum comes in, so the sum from k is equal to 0 to 7, which is that maximum exponent there, of a k times 2 to the k, because 2 is our base. And this is going to give us a 1 times 2 to the 0 plus 0 times 2 to the 1 plus a couple of other zeros plus 1 times 2 to the 4 plus a couple of other zeros plus 1 times 2 to the 7, and this will give us a 145 base 10. Now what do we want to do with this? We want to put it now into our hexadecimal. So 145 base 10 into c base 16. So what do we want to do? We want to say we want to go to powers of 16. So 16 to the 0 is equal to 1. 16 to the 1 is equal to 16. That's still too small. 16 squared is equal to 256. Now this is big. This is too big. So we're going to say that m is equal to 1 because that's the last power that is less than the decimal. So we're going to set m equal to 1, and then we're going to start our division. So we're going to say 145 divided by 16 to the 1. We're starting at 1. This is equal to 9 remainder 1. This is integer division. So we're going to put our 9 in the string, and then the 1 will be carried down. So the 1 divided by 16 to the 0 is equal to 1 remainder 0. And I'll just highlight the thing so you guys can see it. So that 1 is the same as that 1. All right, so 1 remainder 0, and so since now the power is 0, we stop there, and now then we just put the 1 at the end, and that's our hexadecimal. So C16 is equal to 91 base 16, which you can also see as 0x91. All right, let's go the other way around. Let's go from hexadecimal to binary. Let's say that we have a hexadecimal number B816, and we want to convert it to C base 2. So first step, we want to go from the hexadecimal to decimal. So B8 base 16 to B base 10. Once again, we label this with 16 0 and 16 to the 1, and then B base 10. I'm just going to skip the summation notation here, and we're just going to say 8 times 16 to the 0 plus B. Now B is equal to 12, because, well, 12 in decimal. That's just because of the way the numerical structure was designed. So you have A through, once again, you have 0 through 9 for hexadecimal, and then you also have A through F, and you just continue counting from there. So 8 times 16 to the 0 plus 11 times 16 to the 1, and you're going to get a 184 base 10. Now, what we do with this is we want to convert this to now base 2. So 184 to C base 2. Let's do our powers of 2. So 2 to the 0 is equal to 1. 2 to the 1 is equal to 2, and you keep going. You get 2 to the 7 is equal to 128, and 2 to the 8 is equal to 256. And now we can declare that m, that highest power, is equal to 7. So we're going to start our division at m is equal to 7. So this is where the time-consuming aspect comes in, because if that power is high, you have to do a lot of divisions. And there is a trick, though, or a shortcut that you can do at the end. So 184 divided by 2 to the 7 is equal to 1 remainder 56. So our character is 1. Bring the 56 down, or the string is 1. 56 divided by 2 to the 6 is equal to 0, because 2 to the 6 is 64. And 56 is not going to 64, so 0 remainder 56. So now our string is 1, 0. And then 56 divided by 2 to the 5, which is 32. 32 goes in once, and we have a remainder of 24. So we have 1, 0, 1 now as our string. Then 24 divided by 2 to the 4. This is equal to 1 remainder 8. We have a 1, 0, 1, 1. And then 8 divided by 2 to the 3. Now 2 to the 3 is just 8. So this is equal to 1 remainder 0. So our string now is 1, 0, 1, 1, 1. And I'm going to give you a trick right now. If you get a remainder of 0, you can stop with the division. All you have to do is just put that power, the number of zeros left. So put 3 zeros on, because the power is 3. So it's going to be 1, 0, 1, 1, 1, 0, 0, 0. And that is how to convert from hexadecimal to binary. All right, in the programming aspect of things, it's going to be pretty standard. It'll pretty much just follow the algorithm that we outlined. So once again, we want to start with our, I can't type today, our hello world statement. So today let's do a little standard cout hello numbers. How about that? Alright, let's run this, make sure it works. Alright, it does. So there's not really a good way to do this outside of strings in programming, especially if you want to actually see the representation of it, because computers will automatically arrange the bits in hexadecimal. They'll arrange it in binary if you give them those certain different number systems, and they'll just convert it to a text, they'll convert it to a number, whatever the type of the variable is. So we do have to store it in strings, unfortunately, but there's no real other way to do it. So we're gonna have our method. We have to include string as well. We're gonna say standard string convert to base. We'll pass in the string for the original base as an integer, and the new base as an integer. All right. So the way we're going to call this is we'll just say standard string. Let's call it s is equal to. Let's do our example, and that's 100100001. Just like that. I didn't put an equal sign. And then we'll just say standard cout. We want to convert this s from base 2 to base 16. Just like that. All right. So let's actually go through this algorithm now. So first step is we want to convert to base 10. Oops. All right, to start there, we'll have a placeholder. So int y underscore 10, I'm just using the underscore to denote subscript. This is equal to, or let's call it b underscore 10, just to stay consistent with our pen and paper example. So we'll start that at 0. Now we want to do our summation. So we're going to say for int I is equal to 0, and we'll initialize a size variable is equal to og.length, just so we don't have to call this function every time. I is less than size, I plus plus. So essentially we want to get the numerical value ak, and then we want to add ak times the original base to some number, and we'll figure out, we'll go through this step by step. So first of all, to get the numerical value of the character, we can't just parse an integer from a string, because it's not always going to be that. Like I said, with hexadecimal, you go into the letters. So we're going to have some reference that starts at 0 and ends at some letter to store the number of, or the possible characters that we can use. So we're going to have a define macro up here. So define chars, and we'll do our digits first. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then our letters, and I'm just going to stay capital for now. You don't have to put, that's typically custom or standard for hexadecimal, so AB. If you forget your alphabet, I am sorry, but that's too bad for you. Next, we want to have our size, so define number of chars, 36, because there's no real good way to kind of determine the size of that without doing size of, when we can just give it to him right now. So we can have a maximum base of 36 using this character set. So we're going to have our function called that returns integer, and it's called int value, and we take in a character c, and we're going to say for int I is equal to 0, I is less than, or I is less than number of chars, I plus plus. We're going to say, we're just going to test each character. So if c is equal to chars at I, so if the passing character matches that, we're just going to return the index. And if we didn't find anything, we'll just return negative 1 for now. That's fine. Okay. Next is to use that value. So we're going to say b underscore 10 plus equals, or we actually have to get the, so we're going to say plus equals int value of og at I. So we're going to get the ith character and get the integer value. And now we have to raise the, so we're going to say pow of og base. Now we have to raise it to some power. The power we're going to raise it to is because we're going in the opposite direction. Like we started left to right, or we went right to left in increasing powers and started with 0. So we have to do the length minus I, the index, minus 1, just because we started at 0. Just be like that. So OG base, and we raise it to size minus I minus 1. All right, and that should give us the base 10. Next, we're just going to do a little optimization check just to see if the user wanted base 10, we can just return the value. So if wanted base 10, return value. So we're going to say if new base is equal to 10, return standard to string b underscore 10. All right, so let's go ahead and test this out real quick. We'll do that binary string to base 10, and we'll see what we get. And let's compare it with our answer. So we get 145, which is exactly what we got. So we got 145 base 10. Good. All right, for the second part of the algorithm, we're going to go ahead and convert to our desired base if it wasn't 10. So first part of that is find smallest power of new base that is just less than the decimal, and then we're gonna that essentially means the next power is larger than the decimal. So what we're gonna say is we're gonna have our placeholder, so int m. We're gonna have a for loop, so for m is equal to 0, m is less than. So we have to have some kind of upper bound in here. I'm just going to put 100 for now, just to make things a little easier. But you can put any number you want there. As that number's just there, just to make sure people don't enter some crazy number. And then you can actually define a macro, which you can say like define upper bound to 100 and just say m is less than upper bound. And then next you're going to say m plus plus. So we're going to be increasing powers to see what the largest power is. So we're going to say if b10, so if the decimal is less than the power of the new base to the next exponent, we're going to break because we have found that termination condition where the next power is larger. So now that we have m, we can now start constructing the string. So we're going to have a placeholder, so standard string ret is equal to an empty string, int quotient is equal to -1, int remainder, and we're going to be carrying over the remainder, so we're just going to initialize it as the decimal, and we'll see how that works. Next we can do a for loop, so we're going to say for empty first condition, m is greater than -1, so it can be 0, and we also don't want the remainder to equal 0, because once again that's just wasting computation time. If you have if you're just doing 0 divided by some number, it's just going to get you 0. So all you can do is just add the zeros at the end, or put the zeros at the end. So we're going to say and remainder does not equal 0, and then m minus minus, because we're subtracting from the power. So all we're going to say is quotient is equal to the remainder divided by the integer of the power from the new base to m, and then we're going to go ahead and subtract that or something from the remainder. So we're going to say remainder minus equals quotient times the integer power of the new base to m, and all this is doing is just getting the remainder from that division just by subtracting the integer multiplication. And then after that, we just want to say ret plus equals. Now we have to get the character from this. Is a pretty simple way. All you just got to do is say characters at I, or characters at quotient, sorry. Because the quotient will map to one of these letters up here, or characters, so we can just pass that in. All right, and now once we go through the loops enough times, we're gonna have one possible thing where there's gonna be the remaining zeros. Remainder was 0. So we're gonna say if m does not equal 0, and it won't if the remainder was 0. We're going to say for empty first condition, m is greater than -1, m minus minus, And then we're just going to add or put a add a 0 character to the string. Just like that, and then we're just going to say return rect. Now let's go ahead and test this with our example. So base 2 to 16, let's run it, and we get our 91. Now let's try going the other way around just to make sure that the letters all work, and we had a B8 to, and we should get a 91 in decimals. So B8 from base 16 to 2. And we get that number, which does match. I believe 10, yep, that matches. All right, perfect. Yeah, that's number bases and how to convert between them. See ya.